Periodic table. All right, so this is arguably one of the most important things you need to get familiar with when you are studying chemistry, because everything we do involves the elements. When we start doing reactions, all with the elements. So it's time to get familiar with what this periodic table looks like and delve into some of that. So when we have our periodic table, and you can see again part of it behind me there, in the video screen, that everything's arranged according to these chemical properties. And so what's interesting is we see similar behavior with various different groups of elements based on things like how many valence electrons they have and things like that. Some basic information that you will find, okay, is you'll find a whole number that's usually either at the top corner or maybe top center. This is the atomic number. Okay, the atomic number also tells you the number of protons that an element has. So elements, we have three major subatomic particles. We have protons, neutrons, and electrons. Our protons and our neutrons are in the center in the nucleus of the atom, and then the electrons are around the nucleus. Protons are positively charged, electrons are negatively charged. And so we get an attraction from those positive protons at the center of the nucleus and those negative electrons that are floating around. Okay, you'll find the symbol, and you will find the mass. Some periodic tables give you lots more information. Some have the names on them. Some have all sorts of extra information. The periodic table file that I will provide you with the ability to download to use on exams is only going to include these three things that I have labeled here: the atomic number, the symbol, and the mass. They will not contain the name. All right, so when we look at the periodic table, this is its general arrangement here. Now, what's really interesting is you can actually kind of date a periodic table based on how much down here is filled out. Again, anything down there is coming from particle accelerators. And so as we create more elements, we add them to the periodic table. So this one's a few years old because we've actually filled in 110, 111, and 112 now. And I think we filled in 114 and 116. So this one's a little bit older, but the rest of it's still the same. And the ones that we create in particle accelerators, they only exist long enough that we can say, woohoo, we created it. They're not of any practical use whatsoever, nor do we actually have any samples of them. So one of the things that we get on the periodic table is we have groups and periods, okay? So our groups are going to be our vertical columns. Okay, and when we arrange in groups, that's where we start to see similar behavior. Okay, and then we're going to have our periods, which are along the horizontal. Periods are going to be built up based upon what principal energy level we're at, and that's something that we will get more into at another time, what all that means. Now with the groups, what's really cool is some of the numbering of the groups gives us some really important information. So over here, my alkali metals, those are in group 1A. Okay, 1A, we have one valence electron. And that E with a negative, that's the symbol for electron. Okay, so cool thing. Valence electrons, these are the ones that are furthest away from the nucleus. And so again, positive and negative, like they attract each other. But the further something is away from its attractive force, the less it feels it. So the valence electrons, they're the furthest ones away from the nucleus. So they're the ones most readily available to participate in reactions and bonding and all of that stuff. And so when we see a group of elements that all have the same number of valence electrons, well, we're going to see some similar reactivity and similar behavior there. Now, hydrogen, it has one valence electron, but it is not an alkali earth metal. It's a non-metal, and it So that's why it is colored slightly different. So the alkali earth metal, or the alkali metals, are going to be these ones that are in that kind of pink color. So hydrogen is not considered an alkali metal. It just happens to also have one valence electron. Lithium, sodium, potassium, these guys are super fun when you drop them in water. They are very exothermic, so they basically catch fire on the surface of the water. It's really cool. We have to store them in mineral oil because they're so reactive that they will actually react with the water vapor that's in the air. Alkaline earth metals, group 2A. So group 2A, we have, surprise, surprise, 2 valence electrons. Our transition metals, they do some different things. So we're not going to necessarily right now look at how many valence electrons they have. Most of them have 2 valence electrons. Some of them have 1 valence electron, but they have their own unique thing that happens that as we understand how electrons actually exist around an atom and fill around an atom, we'll understand a little bit more about the behavior with our transition metals. When we get back to our main group, group 3A, guess how many valence electrons we have there? We have 3 valence electrons. Group 4A, 4 valence electrons. Group 5A, 5 valence electrons. 6A, 6 valence electrons. 7A are halogens, 7 valence electrons. And then 8A are noble gases. They have 8 valence electrons. This is significant because 8 is the maximum number that we can fit. And so they have a full valence shell. So they're very non-reactive. They don't like to react with anything. We have managed to get them to react, but we have to perturb them quite a bit. I have never personally been involved with any chemistry or research to get the noble gases to react. I just know that we have managed to perturb them. Down here, we have something unique, the lanthanides and the actinides. And so if I were to insert them in the periodic table, we'd get them here and here. So La is lanthanum, Ac is actinum, and so the lanthanides branch off of lanthanum, the actinides branch off of actinum. Okay. And so here you can see some pictures of lithium and sodium. We've got some magnesium and calcium there. And so again, our alkali metals, group 1A, they all have 1 valence electron, similar reactivity. Alkaline earth metals, 2 valence electrons, similar reactivity. Our halogens and our noble gases, so our halogens, 7 valence electrons. Again, similar reactivity. Noble gases, they don't like to react. So what's interesting, neon, this is pretty cool. Okay, so this red color in this sign here, it says Memphis Sounds, Cool Jazz, that actually is neon. So when you talk about neon signs, if it's red, it's neon. But if it's another color, even though we call them neon signs, they're actually not neon. So that hot blues that's written there is not neon. It's another element that's in the gaseous state. So these are actually what we call cathode ray tubes. And so when we can get something in its gaseous state, every element has its own color that we see. Neon was just the first one that we did, and it was the most prevalent, which is why you see a lot of those red neon signs. So here's just a visual of a lot of the different elements. There's this dude, Theodore Gray. He's written some books. He has an app that does some cool stuff. So he's got samples of all the elements, and so this is just a picture of all the known elements. When we get into the stuff that we've created with particle accelerators, you can see when you look at things like BK and CF, berkelium, californium, we don't actually have samples of those. So berkelium, the symbol, the little image he put there is the seal for the University of California, Berkeley. Californium, symbol of California. Curium, a picture of Madame Curie, which is what curium was named after. So when we think about our elements, we have 3 classifications. We have our metals, which is the vast majority of the periodic table. vast majority are metals. We have our non-metals, and then we have our semi-metals. So our metals, these are the ones that are going to conduct electricity well. They're shiny. They are high density, high melting point. Our non-metals, there are way fewer of those. They're not going to conduct electricity. They don't have high melting points. They're dull. They're not as pretty. They don't have the luster to them. Semi-metals, we can also call them metalloids. And so these are metal-like in appearance, but they bridge between the metals and the non-metals. There's a stair-step region on the periodic table. I'll show you in a little bit. And so they have properties that are between metal and non-metal. So they exhibit some metal-like behavior and some non-metal-like behavior. Okay. Most of the elements exist naturally as solids. So all the purple elements are solids. And then we have some elements that exist naturally as gases. So hydrogen, and then stuff over in this region, those are going to be our gases. And then we have two elements on the periodic table that at room temperature, their natural state exists as a liquid. And that would be bromine and mercury. So bromine and mercury are the only two elements that exist naturally as liquids. Now, what's really interesting is we see some trends in behavior. And one of the things that we see is as you go down the periodic table, things get more metallic. And it's really cool. Our halogens here exhibit that behavior perfectly, because when you think about a metal, do you think about a gas or a solid? You think about a solid. And so what's cool with our halogens here is fluorine and chlorine are gases, so very non-metal. Bromine is a liquid, so now we're starting to move into that metal. And then iodine is a solid, and iodine, if you crystallize it correctly, it actually is pretty shiny. It's really cool looking. So we actually see that behavior where we get more metal-like as we go down the periodic table super well with our halogens. Okay. And so this just kind of gives you some pictures that, our metals are, getting to be solid. So strontium and chromium, gold, copper, lead. Those are metals. Those are solids. They're shiny. All right. And then we look at things like silicon and arsenic. So silicon and arsenic are those semi-metals. So you can see here. So we've got this thing going down here. We call that stair-step region. And so these are the elements that are the semi-metals or metalloids that bridge that. So silicon, you can see, it is solid, but it's kind of crumbly. It has a little bit of luster to it, but not a whole lot. And so again, we're kind of bridging as we go between our metals and our non-metals. Carbon, it depends on the state of carbon, the allotrope of carbon. So carbon exists naturally in 3 different states. 2 of them you might be familiar with, graphite and diamond. And so the diamond is only formed at really high pressure and temperature. Graphite is actually the more stable form of carbon. Fun factoid, all those commercials that say diamonds are forever, this is actually untrue. Eventually, infinitesimally slow, a diamond will convert back to graphite, but not in any of our lifetimes, or not in the lifetimes of most of our descendants. But diamonds are actually technically not forever. But anyway, so carbon is a non-metal, but it is a solid. And then as we start moving into things like sulfur, nowhere near as shiny, and then bromine, that liquid, and then iodine. Though bromine does turn to a gas pretty quickly. It has a very, very low boiling point. So sometimes you can be pouring liquid bromine and it can be vaporizing as you're pouring it. Okay. Some elements exist in a molecular form. So most of our elements are going to exist in a monatomic form. Mono, one, they exist by themselves. But some elements exist in a diatomic form, di meaning 2, and some exist in a polyatomic form. So you will be responsible for these. So you can see we've got our diatomics there on the top: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and I've highlighted their location region on the periodic table. And then we have some that exist as polyatomics. Two notable ones there are going to be phosphorus and sulfur. So phosphorus exists naturally as P4, and sulfur exists naturally as S8. So when we start talking about chemical reactions, and I say, oh, solid sulfur reacts with, well, the solid sulfur that reacts is S8. Okay? And then this just shows you where those are in relation to the rest of the elements on the periodic table. Okay, and so again, we have our groups that are our vertical columns and our periods that are our horizontal columns. So I'm going to do a lot with the periodic table. Again, kind of our bread and butter, the periodic table of the elements when we talk about chemistry.